So we're going to talk a little bit about parametric equations and polar coordinates. And you should have learned about these in a prior class, either a pre-calculus trigonometry or a pre-calculus algebra class before you got here. But we'll have a little review of what parametric curves are before we get into the meaty calculus 2 portion of it. So a parametric equation, basically when you think about a particle moving in space or along a plane on an XY plane, if you look at this picture here, you'll notice that the path fails the vertical line test. So in that sense, it can't be described as the graph of a function in the variable of t. However, we can come up with two parametric equations that represent the parametrized curve. So what we'll be dealing with in this unit is we'll have maybe an x equation in terms of t, or f in terms of t, and then maybe a y in terms of t, or g in terms of t. So we could have these two separate functions. The f maybe represents horizontal movement and the y represents vertical movement. When studying motion, as we will be in most of these problems, the t value is going to denote time. Okay, so we're going to have two equations, an x and a y equation, which represent our parametric equations, and they're going to help us build our parametric curve. So let's look at the definition. So here I've pulled in our definition. If we have two functions, an x, maybe we'll call it f of t, a function of t, and y, g of t, a function of t as well. And we look at them on a closed interval of t values. So t is normally going to be specified between an initial and a terminal value. In this case, I wrote a and b. So then all of those xy points, which are developed by looking at the functions, these represent the parametric curve. And that parametric curve is formed by the parametric equations. And then, oftentimes we will have, as I said here, a parameter on t. So parameter, some t between an initial a and a terminal b value. And if we plugged those in, we could come up with an initial point, f of a, for my x value, g of a for my y value, so an initial point on our graph where our graph starts. And the same with b, f of b, g of b would represent our terminal point. So let's do an example. So we're going to sketch the curve defined by these two parametric equations, also considering the parameter, and then we're going to write the equation of the parametric curve. And before we do that, I think it's easier for us to think about what this graph is, what we are looking at here. So let's actually make a table. So what I like to do, consider we have this function, we'll call it f. Function represents my horizontal motion, or x. And then my vertical function, g of t is t, and we're calling that y. So what we're going to do first is we're going to make a table of values. Okay? So in my table, I'm going to list t values. The t is coming from my parameter, and my parameter t goes between 0 and 6. And I can choose as many values as I want between 0 and 6. And choosing more values may help you create a smoother curve. But in this situation, I'm just going to choose integer values. So I have 0, 1, 2, 3, 4, 5, and 6. And I can use those t values to calculate an x and to also calculate a y. And if I know that x and y, I can then create xy ordered pairs. So I don't think we need to write that part of it out here because we'll have our x and y right beside each other. But if I plug all of my t values into my function here, I can calculate these x's. So sine pi times 0 over 2, sine of 0 is 0. And I'll just fill this out for us for the sake of saving some time. All right, so we've got 0, 1, 0, -1, 0, 1. And my y values are the same as t. So I end up with 0, 1, 2, 3, 4, 5, and 6. So if we were to now consider what this graph might look like. So I've got x and y. On my horizontal x-plane, or axis, I have -1, 0, and 1. And then I'm going to count up 6 on my vertical y-axis. 1, 2, 3, 4, 5, 6. I'll try and do this as neatly as I can. All right, so what these points would look like if I would plot them: 0, 0, over 1, up 1, 0, up 2, over -1, up 3, over 0, up 4, over 5, over 1, up 5, and then we've got 0, 6. So what does this function look like? And again, if I had picked infinitely more points in here, I'd have more points to give me a smoother curve. But for the sake of ease, what we see here is we get a curve that looks like this. Okay, so it's kind of like an inverse sine curve. This is what our graph looks like. So if we looked at trying to write these two parametric equations and taking them together and writing them as a parametric curve, well, that would be eliminating that parameter t. So I could do that pretty easily. Since t is equal to y, I can plug y right in for t, and that would give me x equals the sine of pi times y over 2. At this point, I have my function in terms of x and y, but we want to isolate that y value. So this might turn into sine inverse of x equals pi over 2y, or rather 2 sine inverse of x divided by pi equals y. So this is my x, y, this is my function here that represents those together. Of course, it's not a function because it doesn't pass the vertical line test. But if you recall, this is what our sine inverse graph looks like, so it makes sense that I have sine inverse in my function. And thinking about the domain and range of this, since my t values cannot go beyond 0 and 6, my graph, even though our normal sine inverse graph might keep going, this graph is going to stop. So we have a new domain or parameter on x. My x values now exist only between -1 and 1. And my y values exist between, say, 0 and 6. And so that is what a parametric curve is. And we're using two equations that represent functions, two parametric equations, to develop a parametric curve.